There we go. We are recording, and so I will hand over the meeting to Team 6 Incubator to share with us their design.
Awesome. So hello, my name is Carly Taylor, and it's my pleasure to introduce you to my teammates Edward Dumans, Jessica Johnson, Michaela Lamb, Zach Tupper, and Daniel Tremblay, as well as our design, the Incubator. So in this presentation, we will begin with our guiding hedgehog concept before moving through our product overview to key features of the Incubator, subsystem analyses, TRL analyses, and a cost overview. The Incubator is an autonomous microbioreactor developed with the UF Biofoundry with the objective of providing lab equipment at an accessible cost to as many researchers as possible while emphasizing the importance of modular subsystems. So overall, the modular subsystems is what we've really focused on.
So we essentially broke down all 38 of the customer needs and quantified them all if they weren't already done, and decided to break down our design into 5 main subsystems to make sure that they matched all of these needs. Or sorry, I'm sorry, 6 main subsystems. These were the liquid handling subsystem, the liquid handling movement subsystem, the atmosphere control subsystem, the optical density and fluorescent intensity measurement subsystem, the temperature control subsystem, and the culture vibration system, which also integrates the structure in the frame. And so we then categorized all of the customer needs into their respective subsystems where they would match up to make sure that they were all addressed. And then it led to the development of these key features, which we'll further outline in the subsequent slides for each respective subsystem.
Yeah, so now we're just going to talk about a little bit of our product overview. We use the full size requirement outlined in the customer needs, and those dimensions can be kind of seen on the picture. We are going to highlight that sterile and experimental medium control and delivery, that we have robust atmospheric and thermal control. We have an integrated shaker system, and then we are capable of taking OD and FI measurements and readings, and then we have automated most of the processes. The only ones that are not are like refilling fluid tanks. And then the last little point of information is that we have an 85-pound total weight.
Talking a little bit about the chassis of the incubator, we started off with aluminum box tubing frame that's all welded together. This was chosen over some other options like 80/20 because it is a lower off-the-shelf cost for the material. It's also a lot stiffer. A welded joint, it's always going to be stiffer than an angle bracket putting this thing together. It also reduces our assembly time. So also fit and finish of the product, we felt that aluminum box tubing was going to be the better way to go there. The actual bodywork of it is made of sandwich panels that have a thin wall aluminum sheet and styrofoam insulation. Calculating the insulation thickness, we back sized the aluminum tubing size so that they were all flush mounted. So the box tubing and the panels are the same thickness, so it's nice and flush there. The panels are held on by 1/4-20 fasteners that have captive nuts on the backside that are welded to the frame, so it's easy to assemble. There's only 3 bolts that hold each of the panels in. The main point of access is a single door that has a 1/4 turn latch and a gas spring. It opens vertically to not upset the bounding box of the machine, as well as disrupt table space or something like that to move from the side. It's got a door limit switch on the side, which is pictured there, so that the system shut off when the door is open to provide another level of safety. A few other things here. The panels themselves are not meant to be opened or disassembled while the system is moving. The door is the only point of access, but because they are so easy to remove, we felt that was the better solution in terms of serviceability and adding on to the thing. As we improve the design and go into the prototyping phase, it's very easy to service and disassemble.
Zach, I believe you're muted.
So sorry about that.
So what I was saying was that the temperature control subsystem is obviously responsible for regulating the temperature of the atmosphere in the left side of the incubator. So we split our subsystem into two halves, one which contains all of the kind of functional heating and, well, no, it only contains the cooling section. So the pump is in there, the evaporator and the condenser are on that side. And then on the other side is where the actual culturing happens. And so this allowed us to really like effectively have the loads that are placed on the heating and cooling subsystems. So to determine those loads, we set up a basic thermal circuit. As Daniel mentioned before, we are using inch-thick styrofoam, which is sandwiched on either side by 16-gauge aluminum sheet metal, but that's neglected in this analysis because its contribution to the thermal circuit is practically negligible. And then we use that thermal resistance to compute the heat loss at any internal temperature. So at 70 degrees Celsius, it requires about 113 watts, or 113 watts will kind of dissipate to the atmosphere. And then at 4 degrees Celsius, it takes about 53 watts. So that allowed us to select our heating and cooling components correctly. For heating, we're using a cartridge heater in an aluminum casing. It is rated to have a 150 watt capacity, and it has a built-in fan, which allows for just greater heat transfer, and also just gets the air moving in the environment, which is desirable for reasons we'll discuss later. And the coolant is a compressor-based system with just R134A pumping. It's rated by the manufacturer to provide 112 watts of cooling at 0 degrees Celsius, which is below the functioning temperature, so we're well within the factor of safety. It draws 5 amps of current, and it does have error code readouts for if compressor leaks, if there's a problem with the temperature measuring system, and so that would allow for easier troubleshooting.
Similar to the temperature control system, the atmosphere control system is also encompassed in the left half of the incubator, and it allows us to inject and regulate the 5 gases that the customer specified, which were nitrogen, oxygen, carbon dioxide, methane, and hydrogen. And then this is done by attaching external tanks to the hose fittings, and then the pressure is regulated through these regulators. And then the solenoid valves can be controlled based on the feedback from the sensor bank for the gas composition measurement. And that allows a precise amount of the gas to be fed into the PVC delivery system across the system into the right half of the tank, or of the incubator, which contains the cultures. And so it allows us to control the composition of the atmosphere there. And then we also have a rooftop vent to the fume hood, so we don't have any excess gas just going out into the atmosphere. And then we also calculated that if we wanted to completely replenish the atmosphere, if there was any sort of issue with it, at 35 kPa, it would take about 90 seconds to completely replace the gas that's already present there.
Yeah, next we're going to talk about our liquid handling position. So one of our goals as a team was to, instead of reinventing the wheel on some of the subsystems, using solutions that are found to work over and over again and implementing them to this problem and this application. So we decided that a belt gantry would be the best fit for this project. So we're using NEMA 23 motors with timing belts and pulleys in order to do XYZ motion. One also feature to this is that the mounting systems for each axis are very simple and almost blank slates, so that this could be adapted for other needs and other experiments or other desires that the customer may have. Our goal is to make that like a really big point in our design, was to be able to change things out very easily by just having basically 1/4 20 holes that could be mounted and subsystems designed around that. We did do some analysis on this to make sure that the rod sizes that are being used are strong enough. So those rods are made out of steel. And so those are going, we use that calculation using the bending moment and and just a simple putting the z-axis in the middle, and found that we would need like 3.8 millimeter rods. And so we decided to up that to 1/4 inch rods or 6.35 millimeter rods in order to account for any dynamic stresses that were not accounted for in this calculation. And then we'll move on. Yep.
So we're moving forward to the liquid handling subsystem. Our subsystem includes a stepper motor actuated syringe with an approximate precision of around 1%. The NEMA 17 motor with the lead screw allows the syringe to deposit liquid with an approximate max theoretical flow rate of around 900 microliters per second, which well exceeds the customer desire of 300 microliters per second. And then we attempt to address contamination concerns by incorporating standard disposable pipette tips into the design. So when it is time to dispose of a pipette tip, a linear solenoid provides automated ejection. And then with this design, there is potential to incorporate various pipette sizes, as well as potential for an 8-channel pipetter, which would help very much in filling well plates. So that's where we see some modularity with our liquid handling.
Talking about culture vibration a little bit, or shaking more appropriately, one of the primary concerns is that although the subsystem was developed kind of independently, it also had the burden of interacting with a lot of other systems. One of the key things there is our emphasis on modularity. The bunch of cutouts there that you see in that upper picture, those are all a standardized size that accommodate a variety of well plates and conical tubes. So as a result, the footprint of the shaker system had to accommodate at least 8 and that 9 center tray to accommodate our modularity needs. So we're going with an orbital shaker at this point. There are some possibilities to just reverse the polarity of the stepper motors at 180 degrees and make it a pseudo linear shaker, but we've performed some analysis on the orbital only. We feel that based on discussing with the customer and what the shaking patterns really are there for is to not only agitate the fluid a little bit, but also reduce the risk of kind of that outer growth layer of happening on the samples to reduce or impair the OD and FI measurements. We felt that an orbital shaker was more than sufficient given those two constraints. The reason why that's cut out in the bottom is to allow for measurement of OD and FI, so that's kind of why it looks like it does. We're using NEMA 17 motors. There's also some insulation on all of our stepper motors that isn't pictured based on the temperature requirements going to 70 degrees C. We needed to add some insulation there. So it's got a 25 millimeter orbit diameter between the center of the stepper motor and then the arms. If you look at the spec sheets, we're able to go over 200 RPM, but we decided that 50 to 200 RPM brings us within the range that we needed for our acceleration. If you look at other orbital shakers on the market and what they're able to provide. So we're topping out at about 5.57 meters per second squared at 200 RPM. Peak torque at 4 volts with all 4 motors is 12.8 kilogram centimeters. Based on that, we back calculated how much weight this thing could have in terms of its static weight. So based on the weight of the assembly and a 1.15 factor of safety, we're able to add 3.15 kilos of usable mass, aka pipette tips and fluid and conical tubes and well plates. And based on the torque of the motor and the inertia of the system, we can go from 0 to 200 RPM in about 11 seconds. Also talk here a little bit about our adaptability going further into that. So we're able to hold a combination of 8 different conical tubes and well plates. As you can see in the top right corner of that picture, we have these kind of standoffs that hold conical tubes. Those fit in exactly the same size as a standardized well plate. So if you combine the total amount of combinations that we have as well as the slots, we have 72 different combinations of experiments. So if you need to run a lot of well plates at a time, you can run 8 different well plates. If you were just using the machine primarily as a fluid transport device, you can have a bunch of conical tubes, and that orange box there is either a waste or a excess fluid reservoir, and the one on the bottom is our pipette tip rack. The plan is that those will come half empty so that you can use pipette tips, and they will be dispensed in that box as well and fully contained until the experiment is ended, at which point the user can dump those pipette tips and the fluid reservoir into some kind of safe laboratory dispensal place. The primary advantage of this design is it allows for high volume runs. We're not limited to a single experiment. We can actually run multiple experiments at the same time, given the temperature and atmospheric control that our system provides. So we're able to improve the efficiency of single runs, and we don't have to run the machine 5 different times to complete 5 different experiments. We can do it all at the same time if the temperature and atmospheric control constraints are the same.
So I'm going to talk a little bit about the optical measurements. So we use a combination of photodiodes and a laser module to take our measurements. So we have on the liquid movement system, we have this gantry has the laser attached so that the laser can reach each of the well locations. And then we have a bed of optical photodiodes as our sensors, which is how we make our measurement. The optical density makes use of just the laser and the diode. And then for fluorescent intensity, we have an optical filter, which allows us to capture the re-emission in the fluorescent spectrum. And also our design, all of our paneling and gasketing is opaque. So we have a dark environment with which to take these measurements. Here's some specifications for the laser. The power was only 5 milliwatts, but we're able to focus that to a footprint diameter of the 0.79 to get the 1 kilowatt per centimeter squared. The wavelength is 655 nanometers, which is slightly above the customer requirement, but is better suited to the distribution in the filter for our reflection spectrum. And we're able to achieve the flux of 1 kilowatt per centimeter squared. And so I'd like to talk a little bit about the modularity of our system. So we have, for each of the modular spots that we can choose which experiment we're using, we also can choose which kind of photo or optical sensors we use to take these measurements. So none of this is all automated once the users puts them in at the beginning of the experiment. So they would have different sets of sensors based on the distribution of the well locations. So for the 384 well plates, or if you're using conical tubes, and then it's designed for an ease of access through the slide mechanism. So our user interface is an LCD screen, and then there are 8 toggle switches, and we have an emergency stop, which is easily accessible from the front entrance. So if you're doing any kind of work on the machine while it might be on, if you're not removing any panels, the e-stop should be easily accessible. We also have a Raspberry Pi, which is what we're using to run all of our experiments. You can connect your computer to it through this side paneling if you need to do any adjustments or modifications. We're trying to maximize the amount of customization the customer can do, just running the free Raspberry Pi operating system. But when the user, so yeah, that's what we got. The technology readiness level for each system. So we did not feel comfortable assigning anything higher than 3. We know that some of these systems are tested in environments that are similar to ours, but not in our exact application. So the only real test that we have done on each of them is analytical. And so that is why the entire system is limited to a 3 on the technology readiness level. There'd have to be laboratory testing for it to reach any further.
So you can see here the costs of our assembly, and so we're happy to say that we have come significantly under budget. We're really happy with that because that is part of our hedgehog concept, providing a product that is easily cost accessible to a variety of consumers and customers. So it could really be bought by most labs. This would be well within budget. So we're really excited about that. And the way that we were able to keep costs so low was primarily by just using the tried and true methods. You know, there's no need to reinvent the wheel when you're just moving a liquid handling subsystem around. Like people have been doing that for 20 years. There's tons of technologies out there. So and there's no reason to reinvent the wheel with the temperature regulation either. You know, there's a reason that refrigerators use refrigerant. Like, it's cheap, it's effective. So just by, you know, kind of going that way and whenever we can, and also innovating when we can just do it ourselves. Like with the frame, you know, we can just make that ourselves for cheaper than buying some kind of OTS shelf. So by making decisions like that, we've really been able to keep costs low, and I think we're all really happy about that.
Yeah, and just to kind of wrap it up, we're just going to re-highlight some of our key features that we're really proud of. So our optical measurement, just the ability for users, it's very simple, and with it connected to liquid handling, we can reach almost any well plate, and then the choice to add more modulars, those whole assemblies could be purchased more of, and we just started with 2 just to keep the costs low, and then also and allow for users to choose what they want and exactly what they want. So those could be bought and added on if more were desired by the customer. The gantry dispensing system is a tried and true method that's going to hold up and be robust. And with our Orbital Shaker and the modular containers being able to hold so many different combinations, as we see is like 72 different combinations of culture vessels, which is higher than most products right now. And then just having that whole separate side for environmental and temperature control, and being able to add other applications that other customers or they may develop, they want something else controlled later on, and there's a lot of space over there to be able to switch in and out for different requirements as well.
So ultimately, based on all these things, there's really 5 reasons why you should pick the incubator above any other design. The first is Subsystem synergy. Our team made it a focus that the initial prototyping phase was primarily, or not primarily, but we started integrating the subsystems very early on and understanding how we would box things together. Some of the few highlights there that we've talked about, the separated left half and right half side based on the requirements of the systems, the integration between the culture vibration system and the modularity of all the well plates. We really focused on making sure that we had a nice, clean, well integrated design that was something that was seamless and ready for the next phase. The second reason was our large experimental capacity, like we've been talking about before. The ability to run 9 different well plates or things at a time. So 72 different combinations dramatically increases the experimental capacity, so we can increase our sample size, or we can increase the diversity of experiments that we're running at a certain time. Third reason is adaptability. Going back to our hedgehog concept, we wanted to make sure that the incubator was available for direct use at a variety of the UF Biofoundry applications. So that's not necessarily towards one specific researcher, but we believe that our design provides flexibility for everyone that can use it, which is really an advantage of ours above any other. Fourth one, integration of proven solutions. Aside from the OD and FI, there are not many designs that are necessarily unique to ours. We felt that our innovation and our resources were better spent on integrating and packaging and applying those solutions to the current problem, as opposed to trying to find a new problem to solve. Going back to the design process, kind of if a good solution already exists, it is in our best interest to use them and focus on integration and making sure it works directly for application. Last reason is ease of assembly. As a team, we decided it is better to have a more substantial permanent product in terms of the frame and some of the bodywork paneling. So there's very few components that are actually assembled. It's not like you have to build the old frame as the assemble. It comes pretty much all together, which is an advantage of ours in terms of what the researcher has to do when it shows up in the box for the first time. Other than that, thank you all for attending the presentation. We'd love to open it up for questions, but before we do, again, thank you to our corporate sponsors and everyone here for attending our presentation.
All right, thank you. Any questions from our panelists?
I have one. What is the reasoning behind having 4 motors on the Orbital Shaker?
Yes, so ultimately we had to use 4, so there's really 2 reasons. The first is we couldn't use a single centralized motor because it would interfere with our OD and FI system, so we had to have the open cube. The second reason is it was able to quadruple our torque, so it's more efficient than having a single huge stepper motor elsewhere. It more uniformly distributes the axial and radial loads on the motor shafts, and it's just a more cost-effective solution as opposed to trying to source one giant stepper motor with the torque application or the torque requirements that we had.
So
Why not?
what if you just had one motor and supports on the other three with bearings that could just support and provide the same support on the motor shaft, but reduces your cost by 3? And I feel like there's a whole lot more problems if you had 4 motors trying to run simultaneously than one motor with 3 supports.
So we wouldn't have the same torque. We'd have to spec a lot larger of a stepper motor to accommodate the torque that we would need. So we do have quadruple the torque from having store as opposed to buying one that's 4 times as big per se. There's also some slot built in. So what I mean is that only one, there's a master one. So the bottom left one is actually a line fit with the bearings. Everyone else is a clearance fit. So that there's some accommodation for slot because ultimately we're not going to be able to get the stepper motors to run at exactly the same RPM. So they're not all binded fit so that obviously the system would bind if they're all the same.
But wouldn't having that slop in there mean that at some point you're trying to drive one of the other stepper motors a little bit, and so it's not actually going to, like, fundamentally you're correct, but there's the problem of trying, when one motor's pushing, it's now going to impact on the other one. If there's any phase lag there, it's now going to be driving this motor. And when you try and drive an electric motor, it's like you have the inherent resistance in that motor resisting you. So you'd actually need a higher torque until that one catches up, and then you just be clunking around instead of getting smooth motion.
Yeah, so that's certainly a concern. We feel that based on the resolution and the expectation for RPM, the 17 motors are rated at 600 RPM. At 200, we feel that we'll get a pretty accurate control. There's also some closed loop options from the NEMAs. We should be able to measure the output torque. So if we see some kind of current increase across that, we can do some closed loop control there to tune some of the motors out. So something we can do in the prototyping phase is each of the motors that we buy from NEMA, wherever vendor we get, are not going to be exactly perfect. There's going to be some discrepancies. So what we can do is apply some proportional gains to each of the 4 motors to ensure that they're all spinning at exactly the same RPM. And if we can do that and spec them correctly and develop some closed loop control there, I don't think there'll be any issues in the long term.
So once you've done that, have you saved anything over just buying a single higher torque motor?
It's certainly a consideration. I think that another thing to consider is that based on our packaging, we cannot fit a bigger motor based on the liquid handling supports of our system. And based on how big of the tray is, we would have to downsize the actual shaker tray compared to the distance between the tray and the, I guess, the liquid handling supports, which would reduce the overall capacity. So by using a smaller motor, we're actually able to increase the total size of the shaker tray and increase the amount of well plates we have. I couldn't tell you how exactly smaller it would be, but that would be another concern to look at if we use a single motor.
All right, I'd like to say kudos to you guys for talking about stress analysis and not including a FEM. I think you're the first group that's done that, so congratulations. I like to see that. Your enclosure, you said you've got like sandwich panels with the styrofoam core, and they're flush mounted to an aluminum box beam frame.
That's correct. I guess if we could go to a picture of the frame while we're talking about this, but yeah, that's correct.
And you're heating and cooling the entire space around the experiment, so that entire left-hand side of your box is being heated and cooled, correct?
Yes, the left-hand side is, yep.
So if that's sitting at 70 degrees C, what temperature is the outside surface of that box beam at?
Yeah, we've run these calculations, and it barely gets above 25 in almost all situations. The inch-thick styrofoam pretty much like hinders any kind of heat transfer through there. And then there's
Well, you've got box beams, right? So you've got a solid aluminum connection between the inside of the box and the outside of the box, right?
Yes, but none of those box beams are actually they're only contacting the interior culture environment at their corners, if that makes sense.
So do you have some sort of insulation on the inside covering those beams?
Yeah, so not shown in this picture is the top panel obviously is there, and then there's a bottom panel. So yeah, kind of like that. So you can see that the box beams don't actually really come into contact with the culture environment. It's a perfect box of styrofoam, and then only on the very corners is that the box beam corner.
Okay.
Okay, any more questions for this group?
I have a couple, if nobody else does. Elise, Tom, if you guys.
No, go for it.
Okay. You guys mentioned that you went away from the customer requirement on wavelength, and it wasn't much. It was only 15 nanometers. Will that change in wavelength still excite the cells appropriately and adequately?
From what I looked at, there was a paper where they had they were taking fluorescent intensity, and yes, I mean, it depends on which kind of bacteria you have in that experiment. But on the graph there was like a dip, and it was somewhere between like 630, and then it started to go to all the way to like 660. So we assumed that was well within the range.
I would want to see the graph before but yeah, but you guys did it the right way. So
yeah, I can go find it for you if you'd like.
Yeah, I mean, that we can discuss that later. Your assembly time cost, your cost there was like $34, which is less than an hour of labor to fully assemble this.
Yeah, so we the way that we kind of went with that is we used our charts. It's probably slightly a little bit higher than that, but a lot of our alignment, the way we manufacture it is that our manufacturing cost is a lot higher because a lot of these parts are being manufactured and then just put together with either like alignment pins that are just being slip fit over and assembled all together versus having a ton of brackets and things like screws that we have to include into our assembly time. Like, for example, like we don't have very much of other groups have like the 80-20 with all the corner brackets and things like that. And so when we did our calculations, we were a little surprised too, and probably it should be a little bit higher. I'm sure there's something that we missed or didn't account for, but when we did that, because of all the alignment pins versus having everything like just screwed in, because we felt like alignment pins will help with also the structure and the alignment and making sure it's repeatable, then our assembly cost was down.
Cool. All right.
I have a question about the door that you open up. Where do you put it where does it go?
It has a gas shock spring that holds it up.
Oh, okay, cool. That's innovative.
How much force does it take to close that door when the gas shock spring is at its highest force? Because it looks like it's really close to vertical right here, which might be helpful. But also, I'm also a tall human. So a typical lab bench is, Daniel, you're also a tall human. A typical lab bench for me is like below waist level. So if I have something that's a door that's swinging up and being held open, it's going to be in my eyes. So why not have this thing open to the side so it's sitting at 90 degrees open sitting straight out. So it's not, going to decapitate a tall lab technician.
So I don't think it would necessarily decapitate them. But the other thing is that the door opening angle is not going to be 90 degrees. It's going to be almost closer to 180, probably 130 degrees, depending on the angle there. So it's going to be pretty much almost vertical. So it's not going to be, you're going to have to look down a lot. It's going to be well out of your line of sight. The gas shock, I think, is rated for 20 pounds. We haven't done the kinematic analysis, and based on over centering of the pin as you kind of open the door and it swings back, how exactly much force it would cost. The weight of the door, I don't also have the top of my head, but we feel that we could certainly, if we spend a little more time there, source a gas spring that works and is not too heavy to operate. In terms of why we chose the vertical design, we just felt that it interacted the least amount with that. So if I had a bunch of stuff on the other side of the lab table, if it opened 90 degrees, I'd kind of have to go around to get those things. If it opened 180 degrees the other way, it would block the LCD panel. So we felt that in terms of synergy with the other environments, if we were able to open that door up as high enough so it wasn't in your line of sight, it was the best option.
All right, I'm out of questions.
Yeah, I just wanted to say, great job, guys. I really liked that you showed your hand calculations and you backed up your design with your theory, and you actually listed the weight, which was good. I just wanted to say, like, in terms of your presentation, it was kind of hard to follow a little bit about where everything was located in respect to the entire system. So it'd be nice to maybe show like where it's actually located, because it's a little bit hard to follow sometimes. Like the whole procedure of where everything goes and what's automated, what's not. So overall, great job, but it might be helpful to have like a more locational references, I guess.
Thank you.
Thank you.
I did have one comment in general in the presentation, that when you guys were talking about the FIOD sensors, it would have been great to have some sort of a like motion thing that shows where it is in space and how it moves, because it took me a lot of thinking, looking at it going, how does this work, until it took like 3 slides and I was like, oh, now I've got it. So
yeah, I'll add on to that. I mean, it's for me, and maybe it's just me, like just a general concept of operations, and that's not just you guys. That's pretty much every team that I've seen so far. It's real hard to just jump into talking about subsystems before you give the audience kind of an idea of what is it that you want this product to do and how do you expect it to be operated. And I know time's short and there's half an hour for each presentation and you got a lot to get through, but I think that would be extremely beneficial to just basic understanding of how things fit together and what they're going to do.
Definitely. Thank you. Yeah, I think it's the classic problem that, we've been working on this for 5 months now. So it's kind of just like, we don't even think of that kind of stuff. But yeah, it is abundantly obvious that none of this is clear. So, okay, thank you very much for that.
Sure.
It's actually a really great statement, Zach, because yeah, that's the common pitfall of, most presentations, not just here, but like, professionally too, is people forget that the audience doesn't know all the intricacies of everything. So you have to really explain everything. But great job. I liked it.
Thank you.
Thank you.
Thank you. Yeah, that was really good feedback. We appreciate it.
Okay, well, and that's actually a good point to stop on, because we're right at the end of time. So we'll wrap it up there. Let me stop recording.